So now we come to the second approach. The point of this second approach, VQE, is to get by with a much poorer, worse quantum computer by not asking for quite as much. And you'll see how that works by my describing the algorithm. The point of this algorithm is to rely upon the variational principle, which in this context says that if I'm given some state, psi, which is not the ground state, and I measure the expectation value of the Hamiltonian, this full total Hamiltonian with respect to that state, I will get some expectation value, average energy, which is no smaller than the energy of the ground state. So therefore, I might do something like introduce a bunch of parameters in here. Let's call these theta. So theta 1, theta 2, theta 3. And say I use these thetas to manipulate the degrees of freedom I have in the input state to this expectation value. Then again, it will also be no smaller than that. So I might define this thing as the expectation value of h parameterized by some thetas. Okay. Now, you can do this on a classical computer, but the hardest part about the classical computation is preparing this state and then computing this matrix element of h with that state. And the VQE algorithm proposes to do those two steps on a quantum computer. And the rest it does with a classical computer. So here are the steps. Prepare psi of theta, where theta is controlled by your classical algorithm. And this is done on a quantum computer. Measure this h of theta. And there are many ways of doing this measurement, one of which I will describe in a moment if we have time, on a quantum computer. And then third, take this classical measurement result that you now have and run a optimization algorithm. For example, the Nelder-Mead simplex algorithm. Or stochastic gradient descent, or you choose your favorite optimization algorithm, changing theta to minimize h of theta. And go back to the beginning. And this is done on a classical computer. So now we have a hybrid where we have a quantum computer executing some steps and a classical computer executing some other steps. And in fact, you can show that this kind of a variational expectation value is true even if you have a natty density matrix here instead of a pure state. So if your quantum computer starts to devolve and go not so quantum on you halfway through, it still cannot give you an expectation value that's better than the ground state. And there are various versions of these sets of theorems which apply to variances in other quantities that you might want to measure. And so one can try to assert, although it's largely done without proof today, that this algorithm will still work reasonably okay on a noisy quantum computer with not so good quantum bits. And therefore, companies can deliver to you a product which is a quantum computer with poor quantum bits and still expect you to pay a lot of money for it because it could run this algorithm and give you some result. There are not many proofs that it will do so, but it is a very compelling argument and a very interesting direction. And there are now experimental results showing small 1 and 2 gigabit quantum computers doing exactly these steps, the variational quantum eigensolver. So the challenge of this. There are two I would point out most. First, does this expectation value converge? You have to rely upon this classical optimization algorithm to get you better and better values, but you don't have a proof that you actually got the lowest possible value or the desired ground state. Second, this state preparation. It's unclear how this state is actually prepared. There are some ideas of how to prepare this. For example, with adiabatic quantum computation, you start with a beginning Hamiltonian which you can create and try to construct an end Hamiltonian whose ground state is this state that you want to create. And since you have this parameterized, in principle, you have some means by which you can do that. This parameter, by the way, could be things, for example, like the adiabatic path that you use in the quantum computer. Okay, and related to this first challenge is how you measure h. And one way people have done this is to measure the terms of h. So you can say this is actually equal to the average expectation value of h1 plus h2 plus all the way up to however many terms there are in here. So you can measure, in principle, the expectation value term by term in the Hamiltonian. And if the Hamiltonian terms are simple, like Pauli matrices, then you have a feasible way of doing it. Unfortunately, that means that you also now add up the error from each one of these expectation values. And so the error can grow very, very rapidly as you're trying to estimate the expectation value this way. Still, the variational quantum eigensolver is different. We haven't looked at any kind of algorithm like that in class in this semester. How do you utilize a system which has a quantum computer and a classical computer together so that you can get something of the best of both of the systems? How can you make them work in concert so that one hands off information to the other one so that now you can feedback and try to speed up while only have a limited amount of quantum coherence and a limited number of qubits at your disposal? I think this is a fascinating topic. I want to leave you with that challenge. And I want to also leave you with a challenge of thinking about how you can relate Hamiltonians and quantum algorithms. I described the Grover algorithm to you and said you can find a Hamiltonian for Grover's algorithm. Why don't you try this one for fun as well? What is a Hamiltonian for Peter Shor's algorithm for quantum factoring? Can you write down a Hamiltonian for the quantum Fourier transform? I'm not going to give you the answer to that, but think about this. And I hope that in doing so, you will cross many different bridges and divides, which are now what the entire community is talking about, and what the future of quantum computing will dwell upon.